Now, I'm sure all of you are just rounding down to the end of the school year, and if you click this video, you're likely signed up to take AP Calculus next year, and you're likely wondering just what you're getting yourself into. Well, if you're to simplify it, you can boil calculus down to two ideas, just two, derivatives and antiderivatives. Now wait, stop. Don't let those big words scare you off. You'll learn what they mean eventually. Let's start off simple. This is a graph of y equals x. You know where it is. It's a straight line, and its slope is 1. Now, a slope, rise over run, is generally something that tells you how fast the values in a function are changing. And you might have thought that you can only figure this out for linear functions. But however, using derivatives, you can find out the slope at any given point on functions that are not necessarily linear. Now, I won't get into the conceptual stuff today, but here is the function, x squared. That's a terrible x squared, but that's fine. Now, the derivative of x squared is 2x. Using that formula, I can find that at the point x equals 2, the slope of x squared is actually 4. Mind blown. Now, this actually has some real-life applications. Let's say I'm running down the street with a speed of 10 miles per hour. And my acceleration is, let's say, -2 miles per hour squared. Using derivatives, I can figure out my speed every second along the way, because a derivative helps me find how fast something is changing. In other words, it helps me find how fast my position is changing. Now, the second part of calculus is the antiderivative. So let's start by looking at some basic two-dimensional geometric shapes. We have rectangles, circles, and triangles. The list goes on. Now, hopefully, we all already know how to find the area of shapes like these. We have handy formulas for that. So for a triangle, we have 1/2 times height times base. For a rectangle, we have just the height times the base. And for a circle, we have 1/2 pi r squared. Now, I could actually go off into a whole other tangent about circles, but let's just stay focused for now. So now, the other day, let me get this stuff out of the way. So the other day, I was actually looking at my sister's homework. She had to find the area of a shape like this. And I'm sure you already know how to do this. It's literally just 3 different rectangles. Find the base times the height of this one, find it for this one, and for this one, and bam, just add the 3 of them together, and you'll get the area of this shape. Now, what if we get into more complicated shapes? Now, let me just draw. Oh, I still need to get. That's fine. Now, let me just draw this. All right. So I'm sure you have no clue what this is, and that's good because I just made it up on the spot. Now, do you want to find the area of this? Well, using antiderivatives, you can actually find areas under curves. And by that, of course, I mean functions. So let's take x squared. And this is x squared. So now, the antiderivative of x squared, and again, I won't get into the conceptual stuff, it's 1/3 x to the third. And let's say I want to find the area from pretend this is okay. Let's say I want to find the area from here to here. So now to do that, I would just plug 2 into this equation right here. 1/3 And using that, I found out that the area under the curve of x squared from 0 to 2 is 8/3. And now, remember those 2D shapes I was talking about before? Well, the next step in that, of course, is 3 dimensions. So we start with squares, and eventually the 3-dimensional version of that is cubes. We have circles, and the 3-dimensional version of that is cylinders. And so for the area, for 2-dimensional shapes, we have to find the area. But for 3-dimensional shapes, we find the volume. So for squares, we use the formula base squared to find the area. And for cubes, we use the formula base cubed to find the volume. We multiply by the 3rd dimension. And the same exact thing happens here. Of course, for a circle, the area is 1/2 pi r squared, and the cylinder is 1/2 pi r squared times the height, because that's the 3rd dimension. And so if we take the area under curve and the same way we added a 3rd dimension to squares to make cubes, we added a 3rd dimension to that area and made it into a 3-dimensional shape somehow. Now can we find the volume for that? Well, yes, because we have the antiderivative. Thanks to mathematicians of the past, the calculus can help us find, using the derivatives, we can find out how fast something is changing, and using antiderivatives, we can find out the area under a curve.